wasn't there.
Just worrying about that. No, it's technically there it is. But I want to start out first with a little piece of notation that's probably is familiar to most of you, but maybe not. And anyhow, I really like to summarize it. I'm talking about the measurement of angles. How do you tell somebody how big an angle is? So there's the angle theta. Traditionally, we measure angles in degrees. We were all taught in grammar school, you slap down a protractor with a hole at the center here and read off how many degrees it is. In degrees, the entire circle, an entire revolution about here, is divided into 360 equal parts. So the whole circle around here is divided into 360 equal parts, and we call those degrees. How come 360? I was told in grammar school that it's 360 because the ancient Babylonians, who I guess imposed this notation on us, the ancient Babylonians thought there were 360 days in a year, and that's why 360 degrees. I don't know if this is right or not. I never understood what the number of days in a year has to do with measurement of angles. Moreover, they were wrong. I can't believe that the Babylonians were off by 5 days. You know, there's 365 days in a year. It's actually 365 and a quarter. Well, thank God they didn't divide the circle up into 365 and a quarter degrees. That would have been perfectly reasonable, but a whole lot tougher to work with. 360 is not a bad number, but my only point is it's totally arbitrary. This is a stupid damn way to measure angles. When you think about it, yes, we're all used to it, so we don't. I mean, why 360? It's really ludicrous. There is a good way to measure angles, and that's radians.
No.
Yes. Good because not arbitrary. If we talk to civilizations coming from Alpha Centauri, they're going to measure angles in radians. I'm willing to bet. I mean, the idea that they might divide the circle into 360, pretty damn unlikely. But if they measured in radians, I think any advanced civilization is going to do business this way. How do you define an angle in radians? You take the angle in question, get yourself a compass, stick a point down there, mark off the arc of a circle. The arc length here, which I could measure by putting a little piece of string down there or something and then straightening it out and measuring it, the arc length S divided by the radius of the circle in question is the angle in radians. You can't quarrel with that, that's the definition. Theta equals S, the arc length, divided by R, divided by the radius R. That's the definition of angle in radians. Now, the first time somebody told me that, I said, no, this is absurd, because somebody else might come along here with a different compass set at a different radius, and mark off a radius that's somewhat larger. They're going to have a larger arc length. Yes, but they're also going to have a larger radius, right? Larger radius, and the ratio, because they're in exactly the same proportions, the ratio of the arc length to the radius is going to be the same for anybody who draws a circle there. A small one, both numbers small, but the ratio the same. Large one, again, exactly the same ratio. That's the beauty of radian measure. It's unambiguous. Everybody's going to get the same answer there. And there's nothing arbitrary like chopping things into 360 degrees, just arc length over radius. It is actually a beautiful way to measure angles. Incidentally, if you study calculus, or just from what we were talking about the other day, that the derivative of sine and cosine, d by dt of sine t is equal to cosine of t, and d by dt of cosine t is minus the sine of t. Those two formulas are predicated on the assumption that you are measuring angles in radians, and not true if you measure angles in degrees. And for purposes of physics, we always measure angles in degrees unless somebody, in radians, unless somebody has explicitly told you otherwise. If somebody says, this angle is 90 degrees, then you're right, they're not talking about radians, they're talking about degrees. But if they say this angle is 3.2, they're talking about radians. Assume that all angles are in radians unless degrees are specified. By the way, how many radians in the full circle? How many radians corresponds to 360 degrees? 2 pi radians. Is that clear? Because if I go all the way around, what's the arc length?
2 pi r.
It's 2 pi r, the circumference of that circle. So theta would be 2 pi r over r. The r's cancel out. I just get 2 pi. So the total number of radians in a full circle is 2 pi. There's the conversion factor. This is not something that you ever want to memorize or even write down in a book anywhere. It's quick. 360 degrees converts to 2 pi radians. That tells you what the conversion factor is. What is this angle here? In degrees, 180. In radians, pi. How about a right angle? 90 degrees, pi by 2 radians. 45 degrees, pi by 4, and so on. Good way to measure angles. By the way, I have written here RAD, RAD, RAD. But what are the units of angle in radians? The units are length over length, meters per meter. In other words, no units at all. Radians in angles in radians are dimensionless. I don't need to write this RAD. It doesn't tell me anything because radians are dimensionless. Some people like to put their RAD kind of to remind the reader or inform you right at the moment I'm talking about an angle. So sometimes when you want to convey that message, it's handy to write the RAD down there just as a reminder. This is an angle I'm talking about now. But as far as units are concerned, it doesn't do anything for you. And watch out for this, because later on you're doing some horrible long calculation, and the answer, which should have come out in meters per second, is coming out in radians cubed meters per second or something. You say, what is the radians cubed doing in there? Nothing at all. Radians are dimensionless, and actually you might as well not have put them in there in the first place. So if you like to check your units, remember that radians don't have any units. They're pure, an angle is a pure number in radians. How many of you are completely familiar with gradients already? Essentially all of you. Okay, good. For some reason, I believe a book saves the whole subject until much later in the course, and that if you do business that way, it means that I'm going to make inadvertently use gradients from time to time without realizing that they weren't on the table yet, so I thought it's better to slip this in right here, and also I need them for the calculation I'm about to do. Okay, circular motion. A beautiful and profound subject, I believe. So imagine that we've got some particle, an object, that's like this tennis ball on a string that's constrained to move around in a circle.
Yay.
Earlier in the course, we talked about motion along a straight line. Now we're talking about CIR. CLE. Yeah. Does that happen to other people?
Yeah.
You're too
I'm
strong.
going to invent a new kind of chalk that doesn't do that to you. So, sorry, I spelled it. Constraint to move in a circle of radius r.
Use sidewalk chalk.
Use what?
Sidewalk chalk.
The fat stuff. If I could get my hands on some, I would. Maybe it's in the bookstore.
It doesn't look strong.
Okay.
Pretty colors.
Or I used to have one of those little devices. It's kind of like a cigarette holder or something. You punch a button, and a little piece of chalk squirts out. It didn't seem to do the job. Okay, suppose you have a particle constrained to move in a circle of radius r. Here it is. I'm going to lay out some coordinates here. Y. So at some particular moment, the particle is up there at an angle, let's say, theta to the x-axis. And this is a circle of radius r. And I would like to label the position vector for that particle. I'm going to do this subject, by the way, totally different way than the book does it, and totally different way than you will have seen the subject treated in high school. The book does it the way, at least, that I was taught circular motion in high school. I'm going to do it a radically different way, a good deal more sophisticated way, actually, partly because I want to illustrate the power of kinematics in vector notation, three-dimensional kinematics. And partly just to show you a more advanced way of deriving the basic result. Anyhow, so what was this the beginning of? Position.
Pose.
The position vector, r, remember that's the location of the particle. R, on my diagram here, there it is. Now, I would like to give you, of course, the x and y components of that. Let's see if I got this great chalk here. The x component would be that, which is r, the length of the vector, times the cosine of the angle. This is the y component, which is r times the sine of the angle. Everybody except read so far? So, what is the vector r? That would be the x component, r cosine of theta times I hat plus r sine of theta times j hat. So far, so good? Let's check it. What is the magnitude of that vector? Magnitude of r would be the square root of the sum of the squares of its components. Square root of r squared cos squared theta plus r squared sine squared theta. I see there's a common factor of r squared. I'll pull that outside the square root where it will become an r. So this is r times the square root of cos squared theta plus sine squared theta. You happen to know what sine squared plus cos squared is?
1.
Useful fact to know. If you're ever in doubt about that, just draw your standard right triangle with an angle theta in here, opposite side A, nearby side B, and hypotenuse C. Then cos sine squared theta plus cos squared theta would be sine squared is the opposite over the hypotenuse squared. That's a squared over c squared. Cos squared is nearby over hypotenuse. So bringing them together, it's a squared plus b squared over c squared. But Pythagoras tells us that a squared plus b squared is c squared. So this is c squared over c squared, or 1. So the statement, sine squared plus cos squared is 1, is nothing but the trigonometric way of stating the Pythagorean theorem. Anyhow, sine squared plus cos squared is equal to 1. Let me write that up here, because we're going to need it several times. Sine squared theta, remember that notation means sine of theta quantity squared, plus cos squared of theta is equal to 1. Useful trigonometric fact. So this is equal to the square root of 1, and the whole answer is r. Is that what you expected? Yes, that says that the magnitude of r, magnitude of the of the position vector, which is to say the distance from the origin, is always capital R. Indeed. So it looks like we're on the right track. Next step, of course, I'm going to calculate the velocity. And I give away the punchline. After that, I'm going to calculate the acceleration. How do you get the velocity vector? Differentiate. Whoops, wait a minute. Stop that. This is for any kind of circular motion. Now I want to specialize. Uniform circular motion. What do I mean by uniform? I mean that this thing is not only constrained to be on the circle, but it's run around that circle at a nice constant rate. We might as well have it go counterclockwise so that theta is increasing as time goes on, and this little spot just moves around here at a constant rate. How would I express that mathematically? Theta, the angle, is getting bigger in proportion to the time. Uniform circular motion. Moving around the circle at a constant rate, in that case, theta is proportional to the time. The proportionality constant, I'm going to call a lowercase Greek omega, because that's the letter that we'll want to use for this stuff later on. Omega times t. Omega is some constant called the angular velocity. It's the rate of increase of that angle theta. It's a small Greek omega. It probably isn't going to kill you in this course if you write that as a W. In fact, most physics students by the end of their first year course are still calling it W. Later on, I write W with sharp points on the bottom so I can tell them apart, because we need W's for other purposes, whereas omega is more or less reserved for angular velocity. So if you can, get in the habit of writing that clearly as an omega and calling it omega, not W. No, it's probably won't give you this course. So everybody agreed so far. That's just a way of saying that theta is increasing in proportion to time. It's just going around that circle at a uniform rate. Okay, let me stuff that into the formula then. An R as a function of t. Now the position as a function of t would be R times the cosine of omega t I hat. I'm just putting it in for theta here. Plus R times the sine of omega t j hat. That's the position vector for uniform circular motion. Now, I come back to the point that I started to do before I had done this important first step, velocity. The velocity vector for uniform circular motion. How do I get velocity vector? In general, differentiate the position vector. So V of t is equal to dr by dt. Now I need to differentiate this. By the way, this is probably why the book doesn't do it this way, does it by the high school method, because they're still nervous about using a little bit of calculus. So if you're nervous about calculus, you learn the way that's given in the book, which actually I'm going to summarize in a minute anyhow. So, dr by dt, let's differentiate this. How does it go? Differentiate this term first. The r is a constant, the radius is thing. Now I need to differentiate the cosine. Derivative of cosine is minus the sine. So minus the sine of omega t. And now by the chain rule, I need to stare at what's inside the argument of the function and differentiate that with respect to time. That pulls out a factor of omega. So the derivative of cosine omega t is actually minus omega sine of omega t. That's in the I hat direction. Plus now we do the j hat direction. The r is a constant. I differentiate the sine of omega t. Derivative of sine is cosine. Minus sine this time. And the derivative of what's inside, so it's the derivative of the sine times the derivative of the argument of the sine, omega t with respect to t is just omega. That's in the j hat direction. Let's tidy this up a little bit because I see that there's a common factor of r and omega in both terms. So let me write this instead. V of t is equal to omega times r. And what's left? Minus the sine of omega t in the I hat direction plus the cosine of omega t in the j hat direction. So there's the velocity vector as a function of time. I've done this purely algebraically, but geometrically, what would the velocity vector look like on this diagram? It would be, for instance, at this moment, v would be pointing like this. So what I've done actually is calculated by differentiation what this velocity vector is. Of course, a moment later it's pointing like this, a little while later it's pointing like this. That's all contained in the sine omega t and the cosine omega t, the changing direction of v. What's the magnitude of v? As long as we've got the vector velocity there, might be interested in knowing what the magnitude is. That would be the speed, actually. And I'll write that just as v without any arrow over it, meaning the magnitude. That's the square root of the sum of the squares. Omega r squared out in front, and now this thing squared is sine squared of omega t plus this thing squared, cos squared of omega t. Ah, how nice. Sine squared plus cos squared again is 1. I get the square root of omega squared r squared, which is just omega times r. Very good. So v, the speed, is omega times r. Does that make sense? What does that tell me? It tells me that the speed of a point here depends on how far you are out from the center. Of course, I would imagine that you were standing on a merry-go-round or something like that, some kind of a big turntable, and you want to know how fast are you going. If you're in close to the center, you're going around a little tight circle, you're not going very fast. If you're way out here, you're going around a large circle in exactly the same amount of time, you're going at a pretty good clip. So that's what this formula says, that the speed is proportional to how far out you are. R. What's the proportionality factor? Omega, the angular velocity. Of course, the faster the thing is spinning, the faster your speed is going to be. But does it make sense that your velocity, your speed should be proportional, velocity too, but that your speed would be proportional both to the angular velocity, how fast the thing rotating, and to how far out you are. So I think the formula makes sense. We could write it also, for future purposes, omega is equal to v over r. There's another way of thinking about omega, the angular velocity, is the actual speed divided by how far out you are. Okay, that'll do for velocity vector, acceleration vector. How do you get it? Exactly the same game again. Differentiate the velocity vector.
We have a question.
Oh, yeah.
In the velocity equals the square root of that expression, how did you remove the negative sign? Is it the negative sign?
It was the sum of the squares, remember? In general, the magnitude of a vector is the sum of the squares, ax squared plus ay squared, and when you square a number, it doesn't matter whether it was plus or minus.
Oh, okay. I thought it was still negative.
Good question. I bet you a lot of other people were confused about that. I should have said that right there. When I squared this component, the minus sign went away. Okay? I was on my way to calculating the acceleration, which I will do by differentiating v with respect to time. Here it is. What do I get? A couple of constants out in front, omega times r. Now I differentiate. Minus the derivative of sine, cosine, times the derivative of what's inside. Pulls out another factor of omega, I hat, plus now the derivative of cosine, which is minus the sine, times the derivative of what's inside, which pulls out another factor of omega. There we are. See how it goes? Let's tidy that up a little bit. I see that there's a common minus sign in both terms and another factor of omega. So I'm going to pull those out in front. Minus omega squared times r times cosine of omega t I hat plus sine of omega t j hat. Right? The minus signs are out in front now. There was a minus sign in both terms. One of the minus signs came from getting to velocity, and the other one came from getting from velocity to acceleration. So both terms picked up a minus sign in the long run. Now you're supposed to stare at this equation and notice something very peculiar. We've seen this quantity r times cos omega t I hat plus sine omega t j hat before. What is it? That's exactly the position factor, right? R cosine omega t I hat plus r sine omega t j hat, r cos omega t I hat plus r sine omega t j hat. This is nothing but r of t. Conclusion, A of t, I can write it very neatly, is equal to minus omega squared times r of t. So something's going in uniform circular motion. The acceleration is always minus omega squared times the position vector. Now let's see what that's the basic conclusion. What does that tell us? Of course, I'm going to do the same as I've done before. I'm going to figure out what its magnitude is, and then talk a little bit about its direction. I wish there was a word for the magnitude of acceleration. You know, it's handy to have speed as the magnitude of the velocity vector. How about Griffiths? The Griffiths. That's it. The magnitude of the acceleration vector. A is equal to the square root of the sum of the square. Well, I can do it much more easily. The magnitude of A is nothing but the magnitude of minus omega squared r. Minus sign goes away when I take the square root of the sum of the squares. It's just omega squared times the magnitude of r. But what was the magnitude of r? Whoops, I erased it. But you remember what the magnitude of r is? It's capital R, isn't that right? Just the distance from the origin. So this is omega squared times capital R. The magnitude of the acceleration vector follows from here. The magnitude of the acceleration vector is nothing but omega squared times the magnitude of r. What happened to the minus sign? Minus sign gets rubbed up when you take the magnitude. So A is equal to omega squared times r. I'm going to write this because it's the most important conclusion here. A, meaning the magnitude of the acceleration, is equal to omega squared times r. Fantastic conclusion. But I would rather write it maybe in terms of v, because omega, at least if you're like me, omega is a little harder to get my teeth into. V, the speed, I understand what they're talking about, meters per second. So let me put that in here. Omega was equal to v over r, as I found from calculating the magnitude of the velocity vector, speed. Omega is equal to v over r, so if I put that in, I would have omega squared, which is v squared over r squared, times r itself. That'll cancel one of them, so A is also v squared over r. That's the way that most physics students remember the formula, that if you're in uniform circular motion, the acceleration is v squared over r. This is the second formula that we've encountered in this course that I personally would commit to memory. The first one is if you're moving in a straight line at constant acceleration, the distance you travel because of the acceleration is 1/2 at squared. I personally just memorized that because it's too hard to work it out in a hurry. But 1/2 at squared for the distance traveled in constant acceleration. Here's a second one that I personally would memorize. If you're going in uniform circular motion, the acceleration, magnitude of the acceleration is v squared over r, the square of the speed you're going at, divided by the radius of the circle you're going around. How about the direction? Well, this says that the acceleration is minus something or other times the position vector. The position vector looks like that, if the particle is at that location right now. Evidently, the acceleration vector points opposite to that. It points in toward the center. How bizarre. If something's going in uniform circular motion, then it has an acceleration in the magnitude v squared over r, and it points in toward the center. We call this centripetal. acceleration, meaning center seeking. So something that's going in a circle is, by virtue of that fact, accelerating in the amount eastward over r and in toward the center. I don't want to oversell this, but for my money, this is a profound and astonishing result. I emphasize that because most of the books and most people are teaching you something, say, well, there it is, you know, as though nothing much had happened. Something astounding has happened. Something without which physics could not have developed. Because you know why? The Greeks thought, for example, that things going in a circle, they just like to go in a circle. So no big deal. They just keep going in a circle. It therefore requires no force, according to them, to keep something going in a circle. That's just what it likes to do. Newton, and probably Galileo before him, realized that if something is going in a circle, it's accelerating. And as we'll see, I guess on Wednesday, if something's accelerating, there better be a force that's doing the job. Acceleration is produced by force. So there has to be a force. So when Newton saw the moon going around the Earth in a circle, he said, there's got to be a force pulling on it to provide that acceleration. The Greeks never even formulated the question because of them, going around in a circle was just what things like to do. You don't need to explain that. Newton realized that there was something to explain there. If it's going in a circle, there better be a force, and I've got to figure out what that force is. Who's pulling on the moon? And that, of course, led to the whole theory of gravity, and from there to all of classical mechanics, really. So I say this is a profound and astonishing result. How could it possibly be when you first tell somebody motion in a circle is accelerated motion? They say, that's nonsense. I thought you said it was going at constant speed. I did say it was going at constant speed. Well, how can it be accelerating then? Well, watch the fine print. What is acceleration? Acceleration is the rate of change of velocity. Velocity is a vector. Vectors have magnitude and direction. If you change the direction of velocity, that constitutes an acceleration every bit as genuine as if you had changed only the magnitude of the velocity. Changing the magnitude of the velocity, speeding up or slowing down, everybody agrees, that's acceleration. Changing the direction of velocity, that too is acceleration, and that I say is profound and not at all obvious. So here's something going around in a circle. At one moment, the velocity points like that. A moment later, the velocity points like that. The velocity has changed, not in magnitude, because by hypothesis, it's uniform speed around there, but it has changed in direction. And a change in direction constitutes an acceleration. And it's been our business today to calculate exactly what that acceleration is. Let me show you now, or remind you probably, the high school way of deriving the acceleration. I don't need to put it down, by the way. I think this is a very good way to derive the acceleration. In fact, if it hadn't been done in the book already, I probably would have done it this way in class. But as I say, I wanted to show you a little bit more sophisticated way of getting a handle on exactly the same basic result. How does one traditionally get this result? Just plain geometrically, without using differentiation or vector notation. Here's the initial velocity at the beginning of this process. Here's the final velocity a moment later when the thing has moved down to there. And let's say that it has moved through an angle theta. Actually, I'll use the angle phi. We don't need that, but that's what the book uses for it. It's moved through an angle like that. Suppose that I stick those two together and figure out what the change in velocity is. Here's v initial. It was pointing directly to the left. If I slide this thing back up so its tail is there, v final looks like this. Isn't that right? And in fact, if you check it out, that's that same angle phi between the initial and the final vector as the angle down here at the center. Now, what's delta v, the change in velocity? Just by vector addition, vi plus the change is the final. So there's delta V, V final minus V initial, if you like. If I slid that delta V back over onto my original diagram, which direction does that point? Answer? There toward the center. You see that? So the change in velocity, the velocity was horizontal here, tilting down here, but the change in velocity pointed in toward the center. Always in toward the center. As this thing moves around, the change in velocity in an interval is always pointing in toward the center. That's the acceleration, and the reason, geometrical reason, why the acceleration in uniform circular motion, the acceleration points in toward the center, the most surprising direction that it could possibly point, I think, naively. Well, if I drew underneath this the other diagram of positions here, here's the original position and the final position, and that went through an angle theta again, and let's let this S be the arc length that it went through in this time interval. So between here and here, it swept out an arc S. I haven't drawn this quite the same angle I see here, but it's supposed to be exactly the same angle. These two triangles, if you will, not quite triangles, they're wedges of a pi, and it's arc length instead of the chord and stuff. So there's some hanky-panky in here, which is one reason why I prefer really the more sophisticated way of doing it, but in the limit is the correct argument. These two triangles, if you will, are similar triangles because they got the same included angle. So delta V over V, arc length over radius, which is the angle phi actually, is also arc length here over radius of this one. But what is the arc length? That's the distance the thing had traveled, and if it's going at speed v, this is equal to v delta t. If delta t is the time it took to swing out that arc s. So this is v delta t over r. If I divide through by the delta t and multiply through by the v, I get delta v over delta t equals v squared now. Aha! V squared over r, which is exactly the centripetal acceleration. So I get change in velocity divided by time interval, which is acceleration, is equal to v squared over r. Is that a more familiar argument? I always found it a little bit slippery argument. I don't know. Whereas the algebraic one that I did before, or calculus one, is absolutely rock solid. That's an argument that you can plug into a computer and just say differentiate this twice, and out will come the answer. There's no ambiguity about it. On the other hand, it didn't illuminate anything much. This argument, I think, tells you why the acceleration is pointing in toward the center, which is the essential, surprising fact. Then the magnitude, v squared over r, is very important from a calculational point of view. But the idea, the basic idea that I think is so profound is that if you're moving uniformly in a circle, then you are accelerating. Understand what's behind this. There's no physics in that statement at all. This was pure geometry. If something is going in a circle, then it is accelerating in toward the center in the amount v squared over r because of geometry, not because of any laws of physics. This is prior to any laws of physics. Why is that interesting? Because it means it applies to every kind of circular motion. I don't care if you're talking about somebody going around in a Ferris wheel, the moon going around the Earth, Jupiter going around the sun, or an electron going around a proton in a hydrogen atom. If it's going in a circle, then it's accelerating in toward the center, and the acceleration is v squared over r. End of the story. It's absolutely universal. By the way, if it's not going uniformly around this circle, suppose maybe it was speeding up or slowing down, then it still has a centripetal acceleration, v squared over r, in toward the center. But in addition to that, it will have a tangential acceleration having to do with the fact that it's speeding up or slowing down. So this result is actually, in a sense, is not restricted to uniform circular motion. It's any kind of circular motion or any little piece of circular motion. If something is going in a curve, then the acceleration in toward the center of that curve is v squared over r. it may or may not have some tangential acceleration at the same time. If it's uniform motion, then it doesn't. But in the more general context, it could. But the v squared over r is still there pointing in toward the center, regardless of whether it's uniform or not. Let me run for you a cute example. Imagine an Earth satellite that just skims the surface. We have this run somewhere where there are too many mountains in the way. So here it is. Here's the satellite. And it's just 10 feet off the surface. Now, make it 3 miles up there so it doesn't hit any palm trees or something. Okay.
Satellite.
Question. What's the period of the orbit? You know what I mean by period? In other words, how long does it take to complete one full revolution? Well, what's the acceleration of this object? It's right at the surface of the Earth. I say the acceleration is g. You say, no, wait a minute, g, that has to do with things that are falling straight down. This thing isn't falling. Oh, yes, it is. That's exactly what it's doing. This thing was going along like this, but it fell toward the center of the Earth under the influence of gravity. Now it's going along like this, but it fell under the influence of gravity toward the center of the Earth. Now it's going like this, but it fell. An object in circular motion, a satellite motion is precisely constantly falling motion. Is constantly falling in toward the center of the Earth, but meanwhile the Earth, in a sense, is kind of moving out from under it. So it's got to keep on falling, and the acceleration of that fall is precisely g. If you're near the surface of the Earth, if this thing is up 20,000 miles, of course it would be different. G is equal then to v squared over r. What does that tell me? V, the velocity, the speed of the satellite, is the square root of rg. V squared is r times g. Square root is root rg. So if I cared to, I could calculate for you what the speed of that satellite is, but that's not what I asked about. I want to know how long it takes to go around. Well, I can get that from v, isn't that right? Because v is how far it had to go, 2 pi r, the circumference of the circle, divided by how long it took to do it. Just t. That's the thing I'm trying to find. That's equal then to root r g. And if I solve for t, that tells me t, moving that up and dividing 2 by that, is 2 pi r over root r g, or 2 pi times the square root of r over g. There's the period of a satellite that just skims the surface of the Earth. I'll tell you that r is 6,400 kilometers. I was going to do the arithmetic here, but the radius of the Earth is 6380 or something like that kilometers. Stick that in there. Stick in 9.8 for g. Anybody happen to know what the answer is? The answer is actually 84.5 minutes. But I calculate that only by knowing the radius of the Earth and the acceleration of gravity at the surface. Of course, if you were up here much higher, then the period is going to be different. How come? Because the acceleration of gravity is smaller if you get further away. But if you're right at the surface of the Earth, 84.5 minutes is how long it takes you to go all the way around the Earth.